Hello, today we will be presenting about electrolytic remediation methods for our remediation presentation for the course of contaminant hydrogeology. Our group members are Camila van Oost, Jenna Lopez, Nina Chappelle, and myself, Shreya Ramesh. Before delving into the specifics of electrolytic remediation, however, it is important to understand the process of electrolysis as a separation method. Electrolysis is essentially the employment of an electrical current in order to drive the otherwise non-spontaneous separation of a substance. An electrolytic cell, of which a simplified schematic is shown here, is the environment in which this reaction takes place. In the picture on this slide, the two rectangles in gray represent electrical conductors called electrodes, which are typically made of metals due to their conductive nature. These are placed in an ionic liquid that can conduct electricity known as an electrolyte. The conductors are connected to a power supply, represented as a battery here. The resulting flow of electrons or current through this connection causes one of the electrodes to become positively charged as electrons leave it. This is called an anode and is represented by the rightmost electrode. Meanwhile, as current enters the leftmost electrode, it becomes negatively charged and is known as a cathode. This causes positively charged cations in the solution to migrate towards the cathode, while negatively charged anions move to the anode as opposites attract. This method is clearly useful in separating or purifying charged media. Electrokinetic remediation is an on-site electrolytic separation or removal method. It uses the basic principles of electrolysis to target contaminants of metallic or organic nature in soil, sludge, and sediment. To put it simply, this method turns the treatment site into one large electrolytic cell, where the contaminant plume in the soil is the media to be separated. A direct current of low intensity is applied in the polluted region bounded by the cathodic and anodic electrodes. This causes the non-spontaneous movement of positively charged contaminants, usually metals and certain organic pollutants, to the cathode. Similarly, negatively charged organic pollutants and anions, such as chloride, cyanide, fluoride, and nitrate, will move towards the anode. This diagram further illustrates the principles of electrokinetic remediation as well as its driving mechanisms. The three processes that spearhead this remediation due to the applied current are electroosmosis, electromigration, and electrophoresis. Electroosmotic flow is the movement of fluids through the spaces in our porous soil media in the direction from the anode to the cathode. Electromigration is the movement of the differently charged ions within this fluid towards the corresponding electrode opposite of its charge. Electrophoresis is the less dominant movement of charged soil particles or colloids through the electric field. We will go into these mechanisms in further detail in subsequent slides. However, there is another important takeaway illustrated in this diagram. Notice that surrounding the anode is an acidic front of H+, while the cathode has a basic front composed of OH-. This acid-base distribution is further useful in mobilizing metal contaminants up the cathode for further collection, removal, transport, and treatment. So, as briefly discussed on the prior slide, electroosmosis is a primary mechanism of electrokinetic remediation. It is essentially the movement of the liquid containing the ions through a charged surface, which is the soil to be treated in our case. It is driven by advection caused by the soil's moisture, and is not as fast as electromigration, but important nonetheless. Electroosmosis is illustrated in the diagram on this slide by the large white arrows, indicated in this figure as process number 1 and circled in neon green. As you can see, the charge of the soil particles are typically negative, and positive cations tend to line up along their surface. When a voltage is applied, this causes the lined-up cations to move extremely fast towards the cathode through the liquid, pulling the bulk fluid along with their movement. This leads to the liquid ultimately moving towards the cathode. While electroosmosis is not as powerful as electromigration of ions to either electrode, it is useful in that this movement can move neutral compounds that would otherwise be left untreated. Electroosmosis is useful in the end result of treatment without removal, where the electrode polarity is reversed periodically so that contaminants can flow back and forth through designated treatment zones between the cathode and the anode. While this doesn't get rid of the contaminant, it can be used to target certain non-ionic organic pollutants on the site itself. Electromigration, however, is the main mechanism of electrokinetic remediation and aligns more with the basic principles of electrolysis, which we demonstrated at the beginning of our presentation. It is defined as the transport of anions and cations through the substrate towards the anode and cathode respectively. On the figure, it is denoted as process number 2, which is once again circled in neon green, and the movement of ions towards their designated electrodes is shown by the dark gray arrows. Ionic transport is largely dependent on the polarity and charge, as well as additional parameters such as soil temperature, moisture, porosity, the applied current, and any additional mobility provided by electroosmotic flow. Importantly, electromigration can help to achieve enhanced removal, in which the ionic contaminants congregate at either electrode so that they can be subsequently removed and further treated off the site. At the electrodes, contaminants can be removed by being electroplated, precipitated out, or complexed through ionic exchange resins. Finally, a more secondary mechanism of electrokinetic remediation is the process of electrophoresis. It works similarly to electromigration, but pertains specifically to the movement of colloids such as soil organic matter, microbial cells, and smaller soil particles. Heavy metals and other pollutants can adsorb onto the particle surface, giving them a bulk positive or negative charge, which causes them to move towards the anode or cathode, depending on their constitution. This movement is illustrated in the figure as the circled process number 3, and shown by the grainier light gray arrows. However, because colloidal movement is slower, more limited due to their large size, and only occurs with certain contaminants, it is therefore not usually considered with the same weight as electromigration and electroosmosis when determining remediation rates.
There are a variety of influencing factors that need to be considered when choosing a remediation method which is best for both your soil and contaminant type. Looking specifically at electrokinetic remediation, there are multiple favorable and less favorable soil conditions which need to be determined before choosing this remediation method. These include moisture content, presence of material within the soil, surface charge, permeability, and porosity of the soil, and finally, the pore water characteristics. It's very important to determine these conditions prior to starting because certain conditions can make the method either extremely efficient and cost-effective or deem the method ineffective. Looking at moisture content, the electrokinetic remediation technique is most effective in saturated soils. In addition, the moisture content should be high enough to allow electromigration, but should still be less than saturation level in order to avoid the competing effects that tortuosity and the pore water content may have. Presence of material within the soil is also very important to determine because the presence of buried metallic or insulating material may affect the conductivity of the soil, which would make this method less effective or require the removal of the material before conducting the remediation process. For surface charge, a negative surface charge is preferable in the electrokinetic remediation method. This makes clays the most preferable soil type because of their negative surface charge. Electrokinetic remediation is also most applicable in low permeability soils, and a porous media is preferred. When looking at the pore water characteristics, it's important to know the pH and conductivity that the pore water has. This is because the pH has an effect on the valence, solubility, and sorption of the contaminant ions, and the conductivity is an integral factor in determining the efficiency of the electrokinetic process. Another influencing factor when choosing electrokinetic remediation is the contaminant type. This remediation method does not treat all types of contaminants, so it's important to know which contaminant is in your soil and make sure that the electrokinetic remediation process will be effective to treat it and remove it from the soil at the percent removal that you want it to be at. Some contaminants that have been known to be affected by the electrokinetic process include heavy metals, radioactive species, toxic anions, dense non-aqueous fade liquids or DNAPLs, cyanides, petroleum hydrocarbons, explosives, mixed organic and ionic contaminants, halogenated hydrocarbons or TCE, non-halogenated organic pollutants, and polynuclear aromatic hydrocarbons. Now, despite this long list, electrokinetic remediation has been known to be most popularly used for heavy metals and organic pollutants, and it's most effective for these as well. In addition, the direction and rate of movement depends on ionic charge, both the magnitude and polarity, so it's important to know the ionic charge of your contaminant itself, as it might change the effectiveness of electrokinetic remediation. And finally, the last influencing factors are the electrokinetic process itself. Both the type of electrode used as well as the voltage are important considerations when choosing this remediation method. For type of electrode used, it's important to note that metallic electrodes are not favorable because they may dissolve and create corrosive products, which may affect the biology of the soil as well as the current biodiversity within the soil. In addition, electrodes made of inert materials should be used. These include carbon, graphite, platinum, etc. And this is because inert materials will not react with the soil and create negative byproducts. For the voltage, in electrokinetic remediation processes, low voltage DC electric fields are used, and we need to make sure that the soil can handle this voltage and will not react or create any negative effects.
Now we are going to talk about the field implementation of electrolytic treatment, including the techniques and the equipment used. The overall design of these treatment systems will vary depending on a variety of factors, such as the kind of contaminants present, the size of the contaminated area, the desired outcome or effect of treatment, amongst other things. However, overall, you can expect these treatment systems to contain electrodes, at least one anode and one cathode, a power source to create an electric field, and wells to house the electrodes. As mentioned previously, electrolytic treatment takes advantage of mechanisms including electromigration and electroosmosis to move and then remove contamination from the groundwater. This diagram on the left depicts the movement of charged particles to the anode and cathode, again known as electromigration. Water particles are driven towards the cathode as a result of the movement of the ions and the negative surface charge of the soil particles, known as electroosmosis. Now we can get into the individual components in a bit more depth. To start off, I will begin with the electrodes. There must be a minimum of 2 electrodes for this process to work, one being an anode and the other being the cathode. The cathode is negatively charged, attracting positively charged ions, while the anode is positively charged, attracting negative ions. The electrodes can be, and have been, made of a variety of different materials, including graphite, carbon, platinum, steel, aluminum, copper, and more. The material used is subjective to the site characteristics, but generally it is preferable to use inert, non-metallic materials. This is because the metallic electrodes can corrode during treatment as a result of the water and contaminants present, potentially introducing new contaminants to the site as well as decreasing overall efficiency. The spacing of the electrodes and their depth can also vary greatly depending on the site, particularly the extent of the contamination. Small plumes may only require 2 electrodes, one placed on either end of the plume, while large plumes of contaminants may require numerous electrodes placed in grids, alternating between layers of cathodes and anodes. The electrodes can be vertically placed in the ground, as seen in the image on the right, or they can be horizontally placed in the ground. The electrodes are then placed in some sort of casing or well. Again, these can vary greatly in design. Slotted PVC and porous ceramic are 2 materials that have been used in the past, such as in this example on the right by Lintec Design. Similarly to the electrodes, it is preferable to use materials that will not corrode or otherwise negatively react with the contaminated water, making PVC and ceramic good choices. It is also important for the wells to be permeable enough to allow the ions to pass through so that they can be removed. In this instance, the anode was surrounded by a linen fabric, and both wells were placed within a packed sand mixture. A power supply must be used to create the constant low-voltage direct current that is applied between the electrodes. The current density between the electrodes is typically on the order of milliamperes per centimeter squared, meaning there is an electric potential difference between the electrodes of a few volts per centimeter. Thus, the power necessary to generate this direct current field ranges from approximately 50 to 250 kilowatt hours per cubic yard. On the right, there is an example of a small-scale ex situ laboratory setup. Here, it is easy to see the DC power supply connected to the anode and cathode terminals. Once the contaminant reaches the electrodes, it can then be removed from the ground. This can be done in a couple of ways. First, some of the contaminant may plate onto the electrodes. In other words, the ions adhere in layers onto the oppositely charged electrode. A diagram of this phenomena can be seen on the left. When this occurs, the contaminant is removed once the electrode is removed from the ground. Commonly, the contaminant is removed by pumping the water from the electrode wells and treating it externally. Precipitation and coprecipitation may be used to achieve the removal of the contaminant ions. Computer systems can be used in electrolytic treatment to control various parts of the system, as well as monitor what is going on below ground. For example, a computer system may be used to regulate and change the settings of the DC power supply, and therefore the electrical current being supplied between the electrodes. When pumping systems are present, such as those to remove water to be treated or to inject fluids into the ground, these may be controlled by the computer system. It is also very valuable for the collection of monitoring data. Many monitoring devices may be used at the site, such as pH sensors, voltage and current sensors, temperature sensors or probes, and water level meters to check fluid levels in the ground. The fast availability of this data allows operation to run more smoothly and for alterations to be made when needed. Overall, this can significantly improve the efficiency of the treatment system. As electroosmosis occurs and water migrates from the anode to the cathode, it is possible for the groundwater to become depleted around the anode. In some instances, this can negatively affect the efficiency of the treatment system, as the water flux helps the ions migrate from one electrode to the other. For this reason, some treatment systems counteract water depletion by pumping water back into the ground near the anode. Sometimes this water is even recycled water that has since been pumped from and treated at the cathode, reducing water consumption and waste. However, it is important to not oversaturate the ground when replenishing the water table. Doing so could actually increase the spread of the contaminant in the ground in a harmful way. In other instances, the depletion of groundwater is a desired outcome of electroosmosis. Sometimes, electrolytic methods are not necessarily used for contaminant removal, but rather dewatering of soils and sludge. This follows the same principles as described previously. This has a variety of geotechnical applications, including dewatering and filtration prior to construction for structural stability. It can also be used to dewater sludge from water treatment prior to disposal. In the diagram on the left, you can see how the water table drops near the anodes as a result of the water flux towards the cathodes. Here are two images showing the site preparation in Fond du Lac, Wisconsin. In the image on the left, you can see an electrode being installed into the ground, as well as additional electrodes sitting on the ground prior to being installed. The image on the right captures the installation of a treatment zone. This project was carried out by Terrain Corporation and will be discussed in more detail later.
Today we're going to be discussing about 4 case studies where electrokinetic remediation has been used. Our first case study is the U.S. Department of Energy Paducah Gaseous Diffusion Plant in Paducah, Kentucky. Site history. The Paducah plant is located 3 miles south of Ohio River and 12 miles west of Paducah. The plant was involved with the first nuclear weapons program in the United States. In 1952, they began enriching of uranium for commercial power plants in the nation. The plant ran continuously and remained the only gaseous diffusion uranium enrichment plant in the U.S. The plant was owned by the U.S. Department of Energy and managed mostly by the Kentucky Department of Fish and Wildlife. Their total area encompassed 3,556 acres of reservation, and about 750 acres were used for the plant facilities. The Department of Energy leased the Paducah processing facilities for uranium enrichment to the United States Enrichment Corporation. The plant supported more than 50 years of uranium enrichment, leading to a huge amount of hazardous, radioactive, and non-chemical sanitary waste in the site. The soil, ground, and surface water got contaminated. Site missions at present. The Department of Energy has cleanup missions, including environmental cleanup, waste disposition, decontamination, and decommissioning of the site, conversion of depleted uranium, and long-term monitoring. The Department of Energy leases the plant to ENVSE, which has been privatized, and now the Nuclear Regulatory Commission regulates the site. Electrokinetic remediation, along with other in-situ methods, is used at this site. The soil at this site has very low permeability, and the contaminants involved were TCE, which is trichloroethylene. The field test work started in January 1995 and ended only in May 1995. The field experiment served as a pilot study to see the electrokinetic effects. Remediation. The site consisted of 4 feet gravel and clay layers over 40 feet of sandy clay loam with inter-bedded sand layers. The hydraulic conductivity of the sandy clay was about 10 to the minus 7 centimeters per second. The test area consisted of 150 square feet area for a depth of 15 feet. Average contaminant concentration was 83.2 parts per million. In this site, steel panels were used as electrodes, and granular activated carbon was used to capture the contaminants as they moved towards the electrodes. The area was split into 4 treatment zones with 2 electrodes 10 feet apart. The treatment zones consisted of granular activated carbon in a staggered arrangement as shown in the figure. The electrodes had 8 steel panels installed next to each other with a gap of half an inch. Each panel was 16 feet long and 18 inches wide. Fluid was circulated with tubes and pumps. A collection system was designed above the soil to collect vapors containing TCE. The test area was subjected to 40A and an initial power of 138 volts for the first month. Then the voltage was reduced to 105 volts. The average electroosmotic flow was 4 to 5 liters per hour. The temperature of the soil started increasing from 15 degrees Celsius to 30 degrees Celsius due to the applied electric field. The voltage gradient varied between 0.35 to 0.45 volts per centimeter. The The removal efficiency was promising since it was around 98%. The level of contamination fell to 1.2 parts per million. The TCE concentration in the carbon treatment zones were high and were replaced. The cost for the complete remediation in this test was 1,310 per cubic yard. The electroosmosis flushes TCE from clay since this clay did not absorb much TCE and allowed the contaminant to move with the flow. Following the success of the small field test, a large-scale remediation was carried out from August 1996 to March 1997. The soil type was the same as the small test field site. The test area had a larger size of 620 square feet and a depth of 45 feet. The groundwater table started at 30 to 40 feet below ground surface. The electrodes were 1.5 in thick, consisting of equal volume of iron fillings and Loresco coke, and were inserted to a depth of 45 feet. The electrodes were 21 feet apart. The iron fillings help in promoting iron corrosion, thereby reducing the hydrogen ion formation which occurs due to electrolysis. The area was split into 3 treatment zones and was a mix of kaolin clay and iron fillings. This setup was run with a constant voltage of 150 volts. As high concentrations of TCE started showing up, the voltage was increased to a 200 volts level, but this led to heating up the soils and the voltage had to be brought down to 120 volts. Results. The voltage gradient was 0.25 volts per centimeter and it moved the water to a speed of 0.43 centimeters per day. The overall efficiency of the technique was 99.7%. TCE, which existed in free phase in the site, was believed to be removed in the same phase. The emissions were insignificant and the complete cost for this remediation was about $80 per cubic yard for a quarter of an acre at a depth of 45 feet. Our next case study is the Naval Air Weapons Station, NOS for short, in Point Mugu, California. Site history. The NOS, located in Ventura County, California, was chosen for demonstrating electrokinetic remediation. The site was under study and the area had been used for electroplating and metal finishing operations. The area of the site was approximately half an acre, including 2 former waste lagoons located in the center. These lagoons were online and were in use between 1947 and 1978, when it received wastewater from the electroplating and metal finishing plants. The plating shop discharged about 95 million gallons of plating rinse solution and some organic solvents into the lagoons. In addition to this, the lagoons were also the dump site for 60,000 gallons of waste photographic fixer solution and rocket fuel. In 1994, an emergency removal action was decided and the surface samples from the lagoons showed high levels of cadmium and chromium, 25,100 milligrams per kilogram and 1,810 milligrams per kilogram respectively, far exceeding the allowable standards, which were 2,500 milligrams per kilograms and 10 milligrams per kilograms respectively in California. Remediation. Before starting the remediation process, many laboratory tests were conducted with the soil samples from the site. These included testing for contaminant and soil characteristics, grain size, distribution analysis, pH, total organic carbon, toxicity characteristic, leaching procedure, cation exchange capacity, and hydraulic conductivity. These tests were followed by determination of electrode placement, migration rates, electrolyte requirements, removal efficiency, and power requirements. This initial laboratory study was conducted by ERDC and Lintec Inc. and showed that the method can be successfully implemented at the site for remediation. The major method of contaminant transport was expected to be electromigration. System setup. The setup consists of an array of cathodes and anodes as shown in the figure to the left. The anode wells are 4-inch in diameter with slotted PVC casings. They were wrapped in a linen fabric woven tight. The well is also packed with kaolinite and sand. The cathodes are 3-inch diameter each with porous ceramic walls. These were designed by Lintec. The site was subjected to 30 volts and 333 amperes for remediation. Continuous monitoring was performed to check for soil heating. The sensors attached to each cell monitored temperature, pH, voltage, and current. Due to public and regulatory concerns, mineral acids, nitric and sulfuric acids were not used in the site. Only citric acid was used for enhancement since it was available readily, environmentally friendly, and was relatively inexpensive. Decontamination issues in the site. The site had sodium chloride presence, and this led to production of chlorine gas along with oxygen at the anode wells. This required additional off-gas treatment in the design system. In addition to this, the metal sulfides present in the site led to the production of hydrogen sulfide gas at the cathode wells. A scrubber system was introduced to treat the gas, and it reacted with sodium hydroxide. To increase chlorine gas removal efficiency, an air sparging system was installed. After 22 weeks, low concentration of contaminants were discovered in some areas, but the progress review showed that some factors were retarding the remediation progress. Further investigation was needed before implementation on a full-scale basis could be considered, and the field demonstration was suspended in 1998 October. Results. After extensive evaluation, it was concluded that the bench scale tests did not accurately reflect the effects that would occur due to the remediation process. This was specifically true with respect to the competing ions having a retarding effect on the pH front development and contaminant transport. The bench tests also could not predict the efficiency or duration accurately. The performance goals was to bring down the contaminant to California state regulatory levels, but no contaminant was extracted during this process, and samples were not collected after treatment. Hence, the target levels were not met. The transport of electrokinetically mobilized contaminants within confined and unconfined areas were not accessed since the performance was poor during the demonstration. The technology had an adverse effect on the organic contaminants of the soil since they showed an increase. Observation. The VOC data indicated an increase of vinyl chloride in some wells. This increase in contamination was mainly due to the dehalogenation process of PCE and TCE during electrokinetic remediation. The site characteristic that was primarily responsible for the poor performance of the remediation treatment was the presence of high chloride concentrations in the soil. The chloride ions retard the development of pH front and in turn slow down the process of contaminant transport towards electrodes. The site conditions thus proved to be disadvantageous for electrokinetic remediation. Our next case study is the Quizkirk Industrial Site in Fond du Lac, Wisconsin, which my partner previously talked about. Now we're gonna see it a little bit more in depth. About the site. The site consisted of high levels of TCE, which also extended under the riverbed nearby. The soil was saturated clay and sealed with extremely high levels of TCE. The site under treatment extended all the way to allow the contamination of half the Fond du Lac River. Before the treatment was started, the soil was sampled and substantial DNAPL was discovered, which was found to be higher than the amount estimated during the initial design phase. Some of the areas had concentrations higher than 1,000 milligrams per kilogram. Remediation. The remediation was started with 2 anodes and 1 cathode. The installations took just 3 weeks, with the electrical and recycle plumbing taking 2 more weeks to be completed. The system was exposed to 208 volts initially. The initial DC output measured somewhere around 190 and 500 A. Once the site started heating up to the operating temperatures of around 50 degrees Celsius, the power was reduced to 110 volts and 450 A. Monitoring of this site was done remotely, thereby saving some operational costs. The entire project lasted over 2 years until 2008. The economic conditions of the state by then started deteriorating, and hence the funding for this site was eliminated in 2009. Results. After the funding was stopped, the post-treatment sampling showed significantly lesser DNAPL concentrations. If the treatment had continued for some more time, it would have been possible to reach the target contaminant levels. More than 2/3 of the total TCE was removed, and the zones of DNAPL diminished. The iron fillings were still existing and continue to contain any TCE that might migrate across by diffusion or convection for years to come. Our last case study for demonstration levels is a creek bed in the U.S. Army firing range located in Louisiana. About the site. The creek bed U.S. Army firing range in Louisiana was contaminated with lead. Lead poisoning occurs due to the accumulation of lead in body tissues. Prolonged exposure will lead to digestive problems, neurological problems, high blood pressure, and kidney dysfunction. In 1996, the Department of Defense supported the Small Business Innovative Research Program in collaboration with West Electrokinetics, Inc. in carrying out a comprehensive study on the lead-contaminated site. U.S. EPA took part in the result assessment from the study. The soils were contaminated with very high levels of lead, and it reached almost 4,500 milligrams per kilograms in some areas. Remediation and results. The pilot-scale laboratory testing was done for the removal of 2,000 milligrams per kilograms of lead from the kaolinite in 1993. The electrodes were placed 1 inch apart in the soil. The total soil specimen volume was about 2 tons, and the process was carried out for 4 months. The total energy cost reached about $15 per ton. At the site of the study, Electrokinetics, Inc. was using Cadec's electrode system that would promote contaminant transfer to the cathode compartment. The contaminants are precipitated or deposited directly. The removal efficiency was observed to be varying between 90 to 95%. The pilot scale studies showed that the lead contaminant concentrations decreased to less than 300 milligrams per kilograms within 30 weeks of processing. The toxicity leaching characteristic values dropped more than 300 milligrams per liter to less than 40 milligrams per liter within the same 30 weeks. Depending on soil type, the lead removal would vary. If the soil contains high amounts of calcium or magnesium, then lead is precipitated in groundwater, and this would impact removal. Clays tend to show high bonding capacity, and they slow the movement of contaminants. On the other hand, in clean silica or gravel, most of the minerals are removed, and lead travels over longer distances easily. The results at the site are promising so far, but full-scale efficiency or cost-effectiveness have not been evaluated yet.
Now we are going to talk about the applicability and limitations of electrolytic treatment methods. Electrolytic methods are typically carried out in situ, meaning at the source of the contamination, or in this case, in the ground. It is typically used to remove contaminants such as radionuclides, heavy metals, and even organic contaminants. The media from which it is removed can be saturated or unsaturated soil, sludges, and groundwater. Because this occurs in situ or at the source of contamination, there is no need to disrupt or remove soil. This makes in situ treatment less energy intensive and less expensive than ex situ treatment. It is possible to target a specific area with electrolytic treatment, as electrodes can be strategically placed throughout and around the plume. It is applicable for treatment of a variety of different contaminants, though the mechanism in which these contaminants are removed varies. For example, metals can be removed by electrolytic treatment because their charge draws them to the anode or cathode. Non-charged particles, however, such as organic contaminants, are transported by an induced flow of water or electroosmosis. Controlling the pH in the ground, as well as using various enhancing chemical agents, makes it possible to broaden the range of contaminants that can be treated with this method. Here is a table showing the removal rates or efficiencies of electrolytic treatment. This table shows results for metallic pollutants such as chromium, lead, and cadmium, as well as organic pollutants such as trichlorophenol and more. Both artificial and natural soils were used to gather this information with varying pH values. Overall, we can gather from this table that the removal rate of heavy metals ranged from 14 to 59%, while the removal rates for organic pollutants ranged from 9 to 61%. Past treatment and studies have also found that removal rates are higher when there is less removal required, or in other words, when less contaminant is present at the site. Unfortunately, there are some limitations to electrolytic treatment. For starters, it is a pretty time-consuming process, so if rapid treatment was necessary, this might not be a good fit. Another limitation is the presence of other ions or contaminants that are not necessarily being targeted for removal, as these can interfere with the electrolytic process. Large metals can actually divert the flow of the current in the ground between the electrodes, making contaminant transport more difficult. Likewise, if there is a higher concentration of non-targeted contaminant compared to the concentration of the targeted contaminant, the current will again be disrupted. This means that the non-targeted contaminant would have to be removed first before the targeted contaminant could be removed by electrolytic treatment. pH is also another limiting factor in this process. The pH of the soil near the anode becomes very acidic, and vice versa. This acidity can accelerate the decay of the electrode, reducing treatment efficiency. This change in pH can also have very negative or adverse impacts on microbial populations in the soil, affecting the overall health of the soil and ecosystem in that area. Low moisture contents can also reduce effectiveness of this treatment method. As mentioned before, the transport of fluid by electroosmosis helps transport contaminants through the soil. Without this moisture present, effectiveness decreases. Deposits in the ground, such as ore deposits, may have high electrical conductivity, again, affecting the electrical field between the electrodes. Finally, this treatment method is particularly dependent on the surface charge of the clay particles being negative. If this is not the case, or if the charge of these particles is altered during treatment, electrolytic treatment may not be appropriate or applicable.
As stated previously, the conventional electrokinetic remediation process is an applicable solution when the method requires a low impact and environmentally friendly solution, as well as needs to be cost effective and efficient. However, this process does present the risk of having side effects such as focusing effects, polarization effects, electrode corrosion, Joule effects, dehydration, as well as the multiple limitations stated previously, which do limit the applicability of this method. Recent research, however, has shown that alterations to the soil and the traditional electrokinetic remediation process can be made to reduce the limitations and even enhance the mobility and removal rate of the method. This enhanced electrokinetic remediation process includes the separation and reaction of the pollutants, electrolyte pH adjustment, electrode optimization, and finally, multi-technology combinations. In this slide, we will take a closer look at the enhanced electrokinetic remediation and the types of adjustments that are made to make the electrokinetic remediation more applicable and take away some of those limitations stated previously. Looking at the separation and reaction of the pollutants, the migration efficiency of heavy metals can be improved through the addition of organic complexing agents. These organic complexing agents will react with the difficult to dissolve heavy metals and form soluble complexes, which is required in the electrokinetic remediation process. The contaminants do need to dissolve. When we are dealing with a heavy metal contaminant, the addition of acid or an oxidant is suitable for their separation. And when you're looking at organic pollutant as a contaminant, the addition of an alkali, surfactant, or co-solvent is suitable for this organic pollutant removal. Another factor of this electrokinetic remediation enhancement was the electrolyte pH adjustment. By adjusting the pH, the migration ability of the pollutants can be improved, and this will eventually enhance the overall removal efficiency of the process. When looking at electrode optimization, this is a method that is mainly used for heavy metal contaminated soils and less for organic pollutants. And finally, we have the multi-technology combination. So for heavy metals as your contaminant, some technologies that can be used are the electrokinetic ion exchange membrane, the electrokinetic electrolyte enhancement, and the electrokinetic phytoremediation. When you have organic pollutants as your contaminant, the multi-technology combinations that could take place are the electrokinetic Fenton method, the permeable reaction barrier, and finally the ultrasonic or magnetic assisted repair technologies. Despite there being current enhancement processes, which were explained previously, there are not yet solutions which address all of the limitations in this process. This figure shows how electrolytic methods are still a fairly new technology and that research is continuing to be conducted, which could eventually broaden the applicability and take away some of those limitations. The figure seen on the right shows the number of scientific publications on electrokinetic soil remediation registered by Thomas Reuter's Web of Science from 1991 until early 2000. As you can see in this figure, it's a fairly recent remediation technology with large increases in research in recent years. As you can see, from 1990 to 1991, there were 0 publications, and now looking closer in the range of 2010 to 2015, we hit over 90 publications. This just shows that looking at the future of electrokinetic remediation techniques and its future applicability, further adjustments to the process can be made to improve the efficiency in upcoming years.
The costs of electrokinetic remediation are difficult to determine, as many efforts to quantify them have come from lab or pilot scale studies. Due to the unique parameters of each site, such as soil quantity and conductivity, contaminant type, space between electrodes, and overall design considerations, it has been found that standardized costs usually underestimate the finances that go into actual field-scale implementation. However, generally it has been found that metals and inorganic compounds range on the pricier side to treat, from $115 to $400 per cubic meter. Organic pollutant treatment is estimated to range from $90 to $275 per cubic meter. This is considering the nuances of different sites, but weighted average costs based on literature for both are about $200 per cubic meter to be treated. Cost can be further broken down, with equipment procurement and installation accounting for about 40% of costs. This is followed by operation and labor accounting for 25% of costs, power expenditure making up around 15% of cost, and site preparation and management of waste and permits accounting for 10% each. The ranges for these values are further shown in the table on this slide.
My partner just went over the costs of electrokinetic remediation, and now we're going to briefly see its availability. At the field scale, it is available and in use, and at the time it's just for dissolved pollutants because there's not enough evidence for NAPLs. And we have a couple of patents, both American and European. We have Prepstein, Louisiana State University, and Geokinetics International. Here is the list of all the sources that we used to come up with this presentation. With this, our presentation is concluded. Thank you so much for taking the time to watch it, and if you ever have any questions, please don't hesitate to contact us. Thank you so much.